it will be covered on the next exam. Okay? What we're doing today is not part of your second exam, the exam on Monday. However, if you want to study it, I think you should study it. Study it. But it's not going to be part of the exam for Monday. Okay. Okay, so section 3 deals with computerized systems. So now, it's too dark. So you guys have learned, I hope, okay, I talked about film and screens and how you process those images and how the light or how the X-rays interact with the film, how it interacts with intensifying screens, the purpose of intensifying screens, etc. Okay, so now we're going to move on to digital systems, and this is section 3. So digital radiography. As always, take a look at the objectives. Okay, there are. And I'll just go over. I never done it for you. I'll do it this time. Describe the various digital radiography receptors and detector systems. So at the end of this section, you should go back on your head and say, oh, this system, this system, this system, this system. You should be able to list them. Explain critical elements used in the different digital radiography systems. Okay, what makes them unique? Discuss limitations inherent in currently available digital radiography systems. You know, what are the pros, what are the cons? So here's the cons. What is a histogram? So in your head, you should know what a histogram is. And what is that histogram related to the image that you will be displaying on your screen. Describe how the display algorithm is applied to collect the data. First, you need to know what an algorithm is, and then how that algorithm is applied to the data that you have and how the image is reconstructed. Okay, explain why digital radiography systems have a greater latitude than conventional film and screen radiography systems. Basically here is saying latitude when it comes to what? The image presentation. And here you can also think of characteristics and qualities of the digital system. Because all along I told you, I mean, film has better resolution, you can have, I mean, there are big glasses, but why is it that people, if it is so good, why are we moving to digital? And so those are going to be some of the advantages we're going to talk about. Elements of digital radiography, very prone to Alera violations. In the other class, we're beginning to look at those effects and radiation effects. Right? And I talked this morning, I talked a little about Alera. And so why is it that with digital systems, if the technology is better, why is it that we're prone to violations? Some artifact problems. So that's it. So that's how you should look at it. At the end of that section, you should go back to the objectives and look at it. Can I answer this? Can I answer all of the objectives? Okay. Historical development. First thing is Fuji Systems in the 1980s, early 80s, like 83, 84, they came out with the first digital system. However, it was not Fuji who developed the digital systems. What do you think it did?
Kodak.
Kodak. In the mid-70s, about 76, 75, and it just happens Kodak didn't see any future. They think there was just too much investing to do. They want to do more. I don't know exactly why, but they didn't see the viability of spending more money and time into the system. And so Fuji from Japan came and said, hey, we'll buy you the technology. They said, okay, we'll give you the patent. Yeah, take it. Give us the money, keep the money, do whatever you want with the technology. later, Fuji came back and look what happened. Did you guys know that hybrid cars were first developed by General Motors in the 70s? Yeah, General Motors developed the first hybrid cars. Yeah. And then they didn't find a use to it, and they decided, well, let's sell it to Toyota.
Oh.
Yeah.
Oh boy. Seriously?
Yeah.
This is not the first time this has happened, Dennis.
Yeah.
It's like we're great
The
inventors.
first
but
CD
we
technologies
don't know how to
were
finish
first
it.
done here.
Don't see
This
long-term
corporation here in
goals.
Redwood City, they developed the first CDs and a bunch of stuff. But they said, well, there's not much going on. They sent it to Sony. I know. All right. In any case, they done really well with those, right? Yeah. And it is what it is. But in any case, the Japanese have done really well. But it's really not their technologies. It's a lot of technologies are, but they really develop the technologies. Once they get them, they make them work. And so there is also smarts in that part too. In any case, so let's go on back here. Nothing against Japan. It's just that a lot of times people think, oh, they're really smart, they're developing all these things. A lot of times they're not. A lot of times they were developed here. Anyway, so when it comes to digital systems in radiography, so once again, they were developed by Kodak. Kodak sells the patent, sells the technology to Fuji. Fuji begins to work on it, and by the early 80s, I think 83, 84, they already have the first digital systems installed in Japan. Not only developed them, but they had them in a hospital in Japan. Okay, by I will say probably the 90s, that technology was back in the U.S. They were selling it to the U.S. So, but they did come up in the 1980s. Today's systems, you have several manufacturers, not only Fuji. Fuji came out with the first systems, but now you have other companies, and what we're seeing is many companies are merging or creating cohorts with other companies. For example, Siemens in Germany, they have contracts with Fuji, and so Siemens works with Fuji, GE works with Kodak. Kodak came back with the technology. They had to buy the technology back from Fuji, and so that's where you're finding that many manufacturers are merged with other companies that have the expertise. And so they incorporate their systems into it. So for example, if you see the GE systems, all their processors, their digital processors are Kodak, etc. And there are many more. This one is Konica. Alpha is involved. A lot of manufacturers are involved. A lot of the companies that do, they used to do film, they are in the digital business as well. So you're going to find many manufacturers and many smaller companies that you've never heard of before. They're also involved here. All right. So the first type of, let's see, what else I want to tell you here? Yeah. The first type of digital systems that came around, they were that's what they are called, indirect photostimulable phosphor imaging plate systems, right? Or CR, computerized radiography. Okay, so when we're talking, the system that we use here, this system here, okay, this is a CR system, and they still nowadays, CR plates are, this is what they are, this is the long name, this is the name that it was given, indirect photostimulable phosphor imaging plates. okay, or CR for short. And so what you have is a photostimulable imaging plates. What is that? What's the meaning of that?
That's sensitive to, that's activated by light. That's right.
Yeah, it's activated by
Photons
is
of
light,
light.
so it can be photons of any type. So these plates are going to be stimulated, okay, or excited by X-rays. Okay, that's one thing. And then they emit light in response to it. The latent image production, we'll take a look at it, how that's done. We'll do that in detail. But it's very different than how it is created in film. Some of you asked me, is it the same kind of technology with what film does? No, totally different. No sensitivity spec, nothing like that here. The image acquisition, after you have the latent image, you know, how you get that information into a visible image, okay? And that's what the reading digital radiography data will do. Because when you have a digital piece of information, before you can translate it into, in this case, an image, or in the case of music, something you can hear, before you can turn it into something that makes sense to our brains, really a digital image is just a bunch of numbers, right? Bunch of numbers, zeros and ones, zeros and ones, zeros and ones. That's what's called digital, right? Because it's two numbers, zeros and ones. That's what you have, okay? So how do we make sense of that? How do we can translate it into something that, to us, is an image? So let's start with this. Later on, we're gonna study DR plates and DR systems, direct radiography systems. But for now, let's start with, and this is historically how it was developed. So the first system that was developed were the CR plates, or photostimulable plates, okay? And this is how it goes, okay? So you have a photostimulable phosphor. So what you have here, okay, and you're looking at it like, that kind of looks like film, that kind of looks like a screen. Well, I mean, you do have, some of the names are similar, okay, but the active ingredients, what makes, you know, what makes this thing work is different. So you have same principles though, okay. So you have a protective layer, okay, because otherwise you get the active phosphors are going to be removed. So you have a protective layer, you have a phosphor layer here, okay, and then here you're going to have a conductor layer. And this is something new. We didn't have this before, okay? And then you have some kind of support layers, some kind of plastic, some kind of polyester here, and other layers here, backing layer, light, shielding layer. But the active, the heart of the photostimulable plate, it is the phosphor. This is it. This two. And then probably the second most important is the conductor layer. Is what's going to happen with the information, with the energy that has been collected here, how are you going to move it out of the plate? So you have a conductor. And so you have the imaging plates. And when you look at an imaging plate, how many of you are using CR in your hospitals? Just John? Just Sequoia is using?
I mean, on a regular basis or at any point? We have it, I mean, but it's like for Scully, or occasionally a tech will just be like, oh, you know, this plate is smaller, let me use it for this, just because it's like hard to get the image, but other than that, no.
Okay, then everybody else is working with DR. Okay, then, all right, then pay attention. More attention than ever before. So let me show you what a photostimulable plate is. So when you look at the CR plates or photostimulable plates or IP plates, they look like this. So when you look at them, this is just an example. There are many colors. Some are purple, some are pink, different colors. But yeah. So for the girls. All right. So when you look at it, it kind of looks like the regular cassettes, right? It looks like the all the screens, but they are not. That's the similarity ends there. And when you open it, there is no film, obviously, and all you have is just this bluish color screen. That's the photostimulable plate. Okay, that's all there is. They are not sensitive to light. I mean, intense light. I mean, if you really expose them to the sun, yeah, then you can start activating the phosphor. But otherwise, they don't. So, which means that if you expose a patient, say you do an X-ray, and then accidentally you drop it and this thing opens, you're not going to ruin the image. The image is not ruined, like with film. With film, if you open that accidentally and then it gets exposed to visible light, that was it. With this, it's not. Okay, so very similar, but that's the end of the similarities.
There's no film inside, right? It's
No
just-
film inside. No film inside. Alright, now we can proceed. Okay, so those are those ones. So now let's take a look. Let's see what we have. A closer look. So we have this layer, the phosphor layer, okay, is going to be about approximately 10 to 250 micrometers. Okay, so very small, very small. It's smaller than the base you had with intensifying screens. Remember that one will be up to about 250. So about the same size as the base, but this is the actual phosphor screen. Okay, and here you have the PSP crystals. These are the actual crystals that emit, that will emit light eventually. You have this is a binder. They are calling this the substance that kind of maintains the crystal floating within this here. Base again, the static layer, reflective layers. We'll talk about all of them. So I just want to. The common phosphors, the phosphors that are commonly used in CR systems, okay, are barium fluorobromide, europium activated, okay, barium fluoroiodide, europium activated. This is what these two dots mean, and this is what europium is there for. Okay, as you can see, let's go back. Let's take a look. So, what is it? Iodine. So take a look. Barium, fluorobromide. Bromide is there again. Remember, what's the characteristic of the halides?
It's light sensitive.
Hmm?
Light sensitive.
Emit light.
They emit light. All of them emit light. And those were the same compounds we use for the intensifying screens. Remember? We use iodine, we use bromide, we use chloride, we use fluoride, right? So we're going to use them again, but the way they're used is going to be a little different. And the compound, I mean, this is a compound, right? You look at it. It's barium, fluorobromide, europium activated. It's a compound. So, but the active, the active ingredient of this formula is going to be here. Here. That's what makes it. That's what going to makes it glow eventually. Okay, and then I'll explain what the function of europium is there. So far, so good?
Mm-hmm.
Okay, all right, but remember, and I said it, I don't know, it's probably my 20th time saying this. With halides, the characteristic with all halides is the emission of light in response to the absorbance of energy. Always, okay? Okay?
Response.
To the absorbance of energy.
The first one, barium, fluoro,
Bromide,
bromide. And then-
europium activated,
Okay, and the second one, barium.
barium, fluoride, fluoroiodide, europium activated. All right, so far so good? Okay. So those are the, so when we look at this, when we talk about the phosphors, the PSP crystals, the PSP phosphors, these guys here are these guys. Okay? All right. So the KH attenuation of these compounds is, so, you know, this is something that also we talked about when we look at the screens. What is important, the average energy in diagnostic radiography is going to be around here, right? 35 to 50 keV, somewhere around there, plus or minus a few keV. 35 keV is the average energy of a kVp, 80 kVp beam. Okay, so if you're using 80 kVp, this is about the average energy, and that's very good because that's the area where these compounds respond to the emission of light. Okay, all right. So more exposure is needed. If applied kVp is outside of this range. So if you are outside of this range, then you might need to compensate with more kVp. One thing, let me say one thing, with CR systems and DR systems, these systems are more sensitive to kVp changes. Not like film, the film responded very well, directly proportional to mass, right? Or I also talked about the 15% rule, remember?
Mm-hmm.
Okay, well, not with computerized systems. Really, not with computerized systems. Computerized systems, 3, 4, 5 kVp make a big change. Okay, so their response is a lot higher than what it was with film. So keep that in mind. Have you noticed that the great majority of images or cases or radiographic exams that you do, few exceptions obviously, extremities and whatnot, the majority are done at least at 80 kVp?
Yeah.
Because that's the range where you have the most activity within the phosphors. Okay. And so, can you go up higher? Yes, you do. Can you go lower? Yes, you do. But in this range is when they are the most active.
So the phosphors for CR is more active in that range.
And DR2.
Okay.
All right. So scatter radiation. PSP absorb more low energy radiation than radiographic film. Okay? And so you have to be very careful. You have to be with CR plates and DR systems, you have to be very careful not to, you have to collimate very tightly. Okay, that's one thing. You have to collimate, always collimate, and you cannot leave a film, like a cassette laying around, say, that was fixed. You cannot leave them around. Say, for example, you go up and do, you're going to do a pourable. And do your pourable, and then you need to do another pourable. Say you do a chest, and now you're going to do an abdomen. And then, if you leave the plate in the room, that plate will be exposed. It will be exposed. That's how sensitive they are. You have to get them out of the room, put them inside and even sometimes if the pourable is too close, they're going to get exposed. Get them outside because they are more sensitive. Okay, too low energy radiation. Closing anymore. There. Okay, so more sensitive to scatter both before and after the exposure to radiographic film. With radiographic film, you know, there were times where you did a pourable, you left it close, even in the room, even in the radiographic room, they were fine if you had enough distance. But this guy's very sensitive, so you need to be careful. Latent image production, okay? So what happens here, the electron, so what I was talking about was just stuff in general. Now we're gonna look at how the latent image is formed, okay? So this is the core of the class today. So, electron pattern is stored in active layers of exposed imaging plate. What is this saying? That you're going to expose the image, you're going to expose the imaging plate, and then the energy is a store, okay? You're going to store it somewhere within the plate is going to be stored. So that's what we're going to take a look at. Fluorohalides absorb beam through photoelectric interactions. Okay, same thing that happened with the phosphors in the intensifying screens. They are going to absorb the X-ray energy, okay, and then this energy is transferred to photoelectrons, okay, and then a bunch of photoelectrons. You guys remember what photoelectrons are? Photoelectric interaction? What's a photoelectron?
Absorbing.
You guys remember what photoelectron absorption is?
Totally absorbing.
Yeah, that's when one goes down and then it emits. It doesn't count.
The electrons get knocked out of like a K shell.
Exactly.
Yeah.
Remember, the photon comes in, okay? Just think about it again. I'm not gonna move on until everybody understands. Ethel Cruz, do you understand?
Yes.
Okay, what's photoelectric interaction?
When electrons get knocked out of the atom
And then what happens?
and then light comes out.
No,
I'm sorry?
no,
No?
not photoelectric interaction.
X-ray photon.
Yeah. What's quantum interaction? Let's review.
Quantum interactions when
Sabina,
X-ray
what is-
photon.
What is quantum interaction?
When an photon comes and knocks out an outer shell electron,
And then what happens?
and light is emitted, or that creates scatter radiation.
And light is emitted?
I'm not quite sure about that.
Christina Kasansky, content.
Haven't reviewed it.
So she's right, it's an outer shell electron.
Yes.
that
She was right up to that
gets
point.
displaced. And another photon is released.
Ethel Cruz, quantum interaction.
I'm sorry?
What is quantum interaction?
I'm sorry, I need a review.
Okay, thank you for the honesty. All right. Ms. Valentino, that was only 3 weeks ago,
I
right?
know, that's so crazy.
Either absorbed, either scattered.
Huh? Okay, I mean, you're in the right track, but tell us more. I mean, come on. Expand.
I know that a recoil is involved.
The recoil electron comes out. That's
John, what is quantum interaction?
When it interacts with one of the outer shell electrons,
What interacts with the outer shell?
the incident photon,
Okay, so you have an incident photon interacting with the outer shell electron.
and then it changes the direction.
It
of
changes
the-
direction.
Of the
So it hits the electron,
Uh-huh,
okay? And then the photon changes direction.
and energy.
depending on the amount of energy that
Okay.
it has,
And
that changes the degree of its path.
okay, and so the energy that had the original photon, what happens to that energy?
The energy from the original photon, it transfers,
We're in the right track.
yeah, the amount of energy that when it changes its direction, it slows it down, and then the difference from how much it slows down is emitted in another photon. No.
Into the recoil electron?
Okay, so so the recoil electron takes a little bit of that energy, because otherwise, if it didn't have that energy, it wouldn't leave the atom, right? Because it's bound. The atom is binding that electron, and so to get it off that bound, you have to knock it off. And so energy is imparted to the electron, okay? And then the photon goes in a different direction. So that's one of the interactions we studied, right?
Yeah.
The other one that we studied was called photoelectric interaction, right?
Yep.
And that's the one I was originally asking, but you might have a few questions like that on your next exam, because that is just too important. Okay, so make sure you review that because you're gonna see it. It's too important. I bet you will have at least 10 questions on your national boards, at least 10 questions related to photon interaction. At least 10, if not more. So I think it's important for me to make sure that you know it. Okay, so just for sure, make sure that on your next exam, you will have a few questions on that. Even though we didn't study it, even though that was part of exam 1, it will be there. And it will be on exam 4, and it will be on exam, whatever exams until we get it. All right, so photoelectric interaction. Cynthia?
We have an incident photon, it knocks out, or it interacts with the, we want a K-shell electron. And then that gets absorbed and it knocks out the electron. And the incident photon's energy is equal to the binding energy of the K-shell plus some of the energy is given off to that photoelectron.
Good. So what you have here, okay, just to paraphrase what she's saying, what you have here is you have a photon coming in, interacting with an inner shell electron, hopefully a K-shell electron. The total energy is given off to the electron. Total energy. You don't have any scatter radiation, and the electron sucks all that energy and leaves the atom. It has enough energy to leave the atom. And that photon ceases to exist. That photon doesn't exist anymore. That's what we have here. That type of interaction. And then you have the cascade. In this case, what is important to us is the total absorption of energy. Okay? Yes, Garrett?
So it's like the incident photon's energy is equal to the K-shell binding energy plus the kinetic.
It has to be greater. It has to be greater. If it is less, it's not going to do anything.
Okay, I'm just trying to relate to some of the math stuff I did in physics to help understand
Think
that.
about it. Think about it. If you have an electron going around, okay, and it is bound by, say, 5 MeV.
Yeah.
Okay. If you come in with 4 MeV, you're not going to do anything. Okay?
Yeah. So
You have to have, in theory, the same energy, but in reality, you need to have a little
slightly
bit more.
higher.
Okay, so it has to be more. But let's go back to the subject here. The subject here, what I'm saying here is the total, the phosphors, okay? The phosphors that I showed you before, okay? Barium fluorobromide, barium fluoroiodide, europium activated. Those guys, this is what they were gonna do. They're going to absorb that total energy, okay? And then, in this case, several photoelectrons are liberated, okay? And then you have even more photoelectrons are going to be liberated by photoelectrons, by more photoelectrons. So you intensify the reaction here, okay? Can we relate now?
Yes.
Okay, good. All right, so liberated electrons have extra energy. All these liberated electrons will have extra energy, okay? Fluorescence, okay, or they get trapped by fluorohalide to create holes. And here's the key. This is what makes them different than the other phosphors we studied with intensifying screens. You're going to create holes. What holes? Spaces. That's what they're talking about, is spaces. You have empty spaces within the atom are created, okay? Now, these electrons, by the way, these electrons do not totally leave the atom. Okay? It's not total ionization. They do not, write it down, do not totally leave the atom.
Okay, so
Do not leave the atom.
okay, the electrons.
Where do they go?
Tell you in just a second. All right. So you have there are traps. Okay, the fluoride crystals trap half of the liberated electrons or more. Okay, they can trap some of those. Some of them will leave, but what is important to us, what I want you to understand, is that some of them don't leave; they get trapped, and that's what europium is doing. Europium will trap them. Okay. Europium sites contain electron holes. In other words, not the same original holes we talked about. Those are holes that are left in the atom, right?
Mhm.
In the halide atom, that's where those holes are. Now, europium has holes. Look at europium. Europium, take a look, right down here is a semiconductor. What is characteristic of semiconductors? We talked a little bit about semiconductors. Yes, Gary.
Semiconductors are like capacitors? No, wait.
Yeah, in that sense of capacitors. Okay, but what was characteristic when I was describing semiconductors?
Store energy.
Nope. They don't store energy.
Moderately conducting electrical charge.
That's the first thing. You hear semiconductor, it means that kind of conduct sometimes, right? Now, when do they conduct? The,
They're heated, they can conduct. You can control them to conduct or not conduct.
okay, all right, but what makes them conduct? When the current is going in the right direction. Remember?
When the current is what?
Magnetism too.
The current is going in the opposite direction.
In the right
Remember
direction.
P's
In a
and
certain
N's?
direction.
Say yes.
Yes.
Okay, if the current is going this way, right, then these guys are gonna flow, right? But what you have on the other side, if the current is going this way, that's why we use them as what? Rectifiers, right? If they're going this way, you have holes here, not electrons. And then the electricity won't move, the current won't move. Because these are not electrons, these are holes. A hole is an empty space, okay? You don't have electrons, you have nothing there. Yes?
Yeah.
Come on, guys. All right, so they are not gonna conduct. It's the same thing with europium. Europium has these holes, okay? But the beauty of it with semiconductors, in the case of europium, the electrons that jump off the halides, they can be deposited into the europium. In these holes, okay, in these holes, these guys, the electrons just come in and poop, 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 and take that empty space.
And then that makes the current
So the holes
flow?
have,
No.
Okay.
We're not talking about current flow
Okay,
here.
okay.
Remember, this is a little tiny microscopic little things.
Yeah.
We're not trying to do we're not using it, in this case, we're not using it for semiconductors. I was talking about semiconductors and current and rectification, so to help you, to remind you of what we had talked about. And remind you that all semiconductors have holes.
or do the holes neither have a positive nor negative charge?
Holes. And, yeah. All right? Okay, that's what I wanted to remind you. Now that you remember that, right? Now let's go back here. And so what you have here is you have these halides, right? Bam! They get hit with this X-ray energy, right? And then they release these electrons, electrons go up. And some of them are lost, but some of them are trapped because you have, if you see our formula here, ding, 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 where is it? Okay, good. See, within the formula, we have europium there. You have this thing there that is attached to the fluorobromide. Okay, and these guys have empty spaces. And think of this, empty rooms, all right?
And
The electrons are looking for a hotel to spend the night, right? And they have empty rooms, okay? And so those who arrive there first, they take the rooms. The other ones, they have to go find another hotel, go someplace else, all right? Okay, so now that you have a room, okay, you can stay there, and you pay. I don't know, this is just coming up right now, guys. I don't know if it's gonna work at the end, but anyway, you pay for a night, you stay there for a night, right? Okay, the next morning they're gonna ask you, 11 a.m., they ask you to empty the room, because they need to clean the room. So, but for now, you can spend the night there. So that's what happens with the electrons that were released by the halide. They're staying there, okay? They're staying there. All right, so here we go. Yes?
So do these liberated electrons, are they in the same umbrella as the photoelectrons, or do those do something else?
No, they are in the same umbrella as the photoelectric, because it's a photoelectric interaction. Yeah. All right, so liberated electrons have extra energy, and so that's why they move up. Fluorescence or get trapped by the fluorohalide to create holes. Okay? So where crystals trap half of the liberated electrons, it's not the fluorohalide really trapping them, it's the europium, okay, that has the empty holes, and so they stay there, okay? And this is the actual latent image. Okay, remember, how was the latent image in film? Just so we can relate it to. Okay, remember, X-ray came in, and then electrons were moved to the sensitivity spec, and then you have some free silver go into the sensitivity spec, and then you had a few silver atoms there. That was the latent image, right? Yeah. Here, what you have is a little different. Here, what you have is the trapped electrons. Okay, they're gonna some of them are gonna be trapped higher, some lower, some higher, some lower. That's the latent image. Think of this. Here's an idea. Have you gone to the flea market and have you seen where, or the exploratorium? You go and they have this things made out of metal, and then you put your hand in it, and you make an imprint.
Yeah.
That's what you're doing here. Okay?
Oh.
This is an imprint, but instead of being the little metal things, you have electrons
Yep.
moving up and down. Like you stick your face, and then on the other side you see. Am I the only one who does that?
Yeah, I know.
Yeah. Everybody sees what I'm saying?
Yeah.
Okay. Yeah. So, and then on the other side you see the silhouette of your face or the silhouette of your hand, right? Where you have your nose is sticking out more because there was more energy, right? So the same thing with the electrons. So think of this as when the plate, when the plate gets exposed, just imagine microscopically here, atomically here, think of the electrons being elevated, some higher, some lower, with the image that you're trying to imprint. You know, some of the electrons are going to be a higher state, some are going to be a lower state. Okay? That makes sense?
Yeah,
Okay, good.
that was a good one.
And that's the latent image. Okay, that's the latent image. So if we look at it, I mean, with graphs, this is what I think came from Bushon. I can't remember. It might be Carl. I don't know. Anyway, what you have here, photoelectric interaction, right? Comes in, you have a photon hitting the electron. Okay, the electron goes up. Okay, and now the europium has a room, has an empty space, and it can hold it there. And it keeps them there, okay? And that's what creates the latent image. Now, and here's the second part of the system. Okay, what I described was how the latent image is created, but at this point, we cannot see the latent image. The computer cannot understand the latent image. Okay, because all you have is a bunch of electrons. Some higher, some lower, that's all you have. And so, but what is characteristic? What is the number one characteristic of halides? Emitting light. Okay, but now, remember, for this electron, which is in a higher state, for it to come back down, what does it need to happen? It will release energy, but for it, remember, if you're out here and you're coming this way, you also have to do something to excite it to come back down. Okay, and in the process of coming down, you're going to emit light, but you have to excite it, encourage it to come back down. And that's what we're going to see in just a bit. But that's what happens. You have the electron here in this electron hole. The electron eventually comes back down and emits visible light. Okay, the visible light, we can look at it, we can read it, you can detect it, okay, and then transform that light into an electrical signal. The electrical signal, now you can send it to an analog digital converter. You split that signal, okay, into digits, you digitize it, and then you can send that information to the computer. Let's take a break, because some of you are really closing your eyes, falling asleep. So let's take a break. Let's take a 10-minute break. Come back at 11.